Hi, everyone. My name is Ingrida Semenec, and I am PhD candidate in Queen's University in Kingston, Ontario, Canada. And I'm part of Snow Plus experiment, which focuses on neutrino detection. And today I will give you a general overview about geoneutrinos and their detection, as well as I'll try to talk a little bit about geology as well as a physicist, so bear with me there, to just give you geology that's related to my geoneutrinos, to give you a motivation for their detection and how I can help with maybe some geology questions. So first of all, let me introduce you a geoneutrino. Geoneutrino is an electron antineutrino particle, which is created via a process called beta decay. So geoneutrinos that we can measure come from mainly uranium and thorium deposits within the ground. For example, uranium could naturally decay into lead and produce electron, and with every electron, it will produce antineutrinos as well. So this process also releases some heat, and that contributes to the radiogenic heat of the Earth. So measurement of these geoneutrinos could be a missing piece in a larger puzzle that geologists have been trying to solve. So what that puzzle is, I'll start with the heat budget of the Earth. So far, in geosciences, we measured the total amount of heat coming from the surface of the Earth, on the surface of the Earth, to be about 46 terawatts. And those 46 terawatts is what's on the surface, and it includes all the different known heat sources, such as cooling of the mantle and core. And of course, this is very simplified. So such as cooling of the interior, due to the primordial formation process, and the radiogenic heat, which is, as I said, heat that comes from radioactive elements inside the Earth that include the beta decay that produces my geoneutrinos. So because we can take samples of the crust, we can know radiogenic heat that we expect coming from the crust pretty well. However, it's really hard to dig deep, and so far we haven't really been, I think, successful of taking deeper mantle layer samples and measuring the amount of radioactive elements we have in the deeper layers of the Earth. So it would be really interesting to measure geoneutrinos and be able to say something about that. Considering that all the mantle cooling and CMB heat flow and the core growth processes, they're being studied, but also have quite large uncertainty so far and still are in development of their models as well. So as a particle physicist, the only information I can attempt to measure so far is this radiogenic heat. I will try to give a bit of geological introduction as a non-geologist, and I'll try to relate it to geoneutrinos as much as I can. So as far as I understand, building the models for the planet's composition is not an easy matter. And currently, the most well-known models for me especially are the bulk silicate Earth models. And from geochemistry and what I care about, we know that there's negligible potassium, thorium, and uranium in core. So for my studies, I'm just ignoring the core. However, if you're a geologist who has a different model for the core, let's say that's made purely of potassium, we can test that as well as soon as we can detect potassium in geoneutrinos. So don't worry about that. But I so far care about these bulk silicate Earth, mainly my lithophile elements, where my potassium, thorium, and uranium are located. The way these models are made is by trying to understand the actual building blocks of the Earth and then attempting to account for the evolution and known geochemistry. I love this plot because I find it really beautiful that it's shown that the composition of chondritic meteorites actually matches the composition of solar photosphere really well. So in this plot, you can see the log abundance of solar photosphere for the different elements and the log abundance of C1 chondrites. And it creates this beautiful trend. And of course, you have some outliers here because noble gases, the sun is really enriched in noble gases, so they're above here. And then also sun burns lithium in its fusion, so it's depleted here. But what this basically gives us is the starting point, the elemental composition of the solar nebula, which gives us the 99% of the mass of the solar system that is sun. Therefore, we can make the assumption that composition of the terrestrial planets are made of the same building blocks. So the composition should be equivalent. I like that. Then it kind of culminates into this beautiful plot. And now that have your general idea of your building blocks from which your planet was formed, you need to understand the difference and how their abundances relate. And I like this plot for that a lot, where we have the y-axis, and this is from Bill McDonald, I believe, this plot. So who's in the room now? So thank you. Y-axis gives us a sort of a reference of abundances of different elements normalized to the composition of those C1 carbonaceous chondrites, because we don't know the absolute abundances of the elements of the Earth yet. And the x-axis is on the top is temperature, and then the bottom of the pressure in pascals, which gives us condensation temperature at which 50% of the abundance is condensed from vapor to a solid phase. So at what temperature these elements start to crystallize out of the solar nebula to start forming a rocky planet. So then the refractory elements are the elements that condense out of nebular disk at high temperatures. And what's really neat about them that empirically they're observed in equal and proportional amounts in the chondrites especially. And thus these ratios are conserved for the refractory elements. And then for the volatile elements, they are more sensitive to the temperature. So you have this sort of a trend that's a bit more uncertain. And consequently, for my geoneutrino analysis, if I can establish the absolute abundances of thorium and uranium on the planet, I can then, we can then try to use the chondritic ratios of refractory elements to set their abundances. And from that, model the remaining abundances of the other elements. And importantly, if we would be able to measure abundance of potassium using potassium geoneutrinos, which sadly so far we're not measuring potassium geoneutrinos, and I'll mention that later a little bit more. We could also establish the volatility curve for the planet as well. So I really, really like this plot for that, because it gives me right away, my uranium, thorium is here, I can possibly measure them. Potassium is here. Hope we will be able to measure that as well in the future. So far, our questions and the answers are, what is the ratio of primordial cooling versus radiogenic heat? What is the distribution of the heat-producing elements inside the Earth? What are their absolute abundances? Could we also further constrain that chondritic ratio between uranium and thorium? And also the potassium geoneutrino detection could help constrain the slope for volatile elements as well. So for the detection of potassium geoneutrinos, this will fall a little bit out of the scope of my prepared presentation for today. However, people are actively working towards improving the technology for us to observe geoneutrinos coming from potassium, but I'll mainly focus on uranium and thorium for today. So how can particle physics help with this? To help you with those questions, we use liquid scintillator detectors. And what a liquid scintillator detector basically is a large volume that's filled with a scintillating material. So that scintillator is a material that emits light that is following the excitation by ionizing radiation, which means if my particle crosses my medium, it'll create light, and then I can collect that light and see it using photomultiplier tubes, or so-called PMTs, which just look like big light bulbs, but they don't emit light. They're really good at detecting light in any really small quantities and turning into the signal for us to then analyze. So usually these liquid scintillated detectors are built underground to reduce backgrounds coming from atmospheric or cosmic rays, as only the most energetic particles, including also neutrinos, that can also reach the detector and interact. Neutrinos, not because they're energetic, but because they are weakly interacting particles, and they can pass through large volumes of dense material and not interact much. So that's why usually liquid scintillated detectors are quite large, and they're getting larger and larger with the coming iterations. So moving on how we actually see these geoneutrinos, antineutrinos in our detector, we can see them via inverse beta decay. So they're made with beta decay, and we can see them via something we call inverse beta decay. So when the incoming antineutrino comes to our detector, decides to interact with a proton, and then that interaction creates positron and a neutron, and positron then quickly, in the timescale of a few nanoseconds, annihilates and creates some light. And then the neutron bounces around for a bit in the process called thermalization for about 200 microseconds and gets captured by a nucleus. In my detector, mainly hydrogen. And that creates another light signal of, which is quite specific in energy, which is 2.2 mega electron volts. So by observing that light, we can count how many antineutrinos we saw, and measuring the prompt scintillation light from positron actually gives us really good estimate of the incident antineutrino energy, which is really nice. However, as I already mentioned, again, we need large volume of these target protons. We also need them somewhere where we have very low other radioactive backgrounds that we don't want to see. And our scintillator has to be very good quality, low in radioactive elements, as well as quite transparent for us to really be able to detect that light. So we have quite a few proposed and running large-scale liquid scintillated detectors around the globe. I don't think I even have all of the proposed detectors here on this slide, but so far, geoneutrinos have only been measured by BOREXINO, which is in Italy, and KAMLAND. So BOREXINO sadly already finished their data taken and is being decommissioned, but it gave us many years of beautiful neutrino data to look at, as well as KAMLAND, which is running. So they've published their results for geoneutrinos already, and I'll be talking about that a little bit, as well as SNO+, which I'm part of, is currently taking data, and I sadly cannot show any results yet because we're still in the process of taking data, but I'm analyzing data as it comes in, and maybe I've seen few already. It's just not enough yet for any publication. So I'm very excited that there will be results soon. So, as well as a Juno, which is in construction, which I'm excited about because you'll have really large statistics because of its large volume, as well as the ocean bottom detector, which you'll hear more about it from Hiroko. So make sure you tune in for that talk. Okay, so to measure the detection for geoneutrinos, we have to understand the production and the detection principles at each separate experiment site specifically, and I'll explain why. Here you can see the energy spectra coming from different radiogenic heat-producing elements that produce geoneutrinos. And for liquid scintillator technology we have now, we can only detect this part of the spectrum that's above this threshold. So we can only see the uranium and thorium, and not even full spectrum of uranium and thorium geoneutrinos, just the end, more energetic end of it. And this threshold is due to the difference in mass between the products of positron and the neutron and the reactants of antineutrino and the proton. meaning only antineutrinos with kinetic energy that's higher than 1.8 megaelectron can participate. So when building the expected geoneutrino signal, sadly, we definitely only just consider uranium and thorium so far. We consider just uranium and thorium abundances according to different geological models, and then account for the rest of the spectrum as expected. So if you're a geologist with a pretty good idea of the element distribution in the Earth, and if you want to test that model using geoneutrino measurements, you need to construct your model and have a prediction for the expected geoneutrino signal given that model. So what you should do, and what we do, is we construct the Earth, divide it into many layers, and then we calculate the geoneutrino flux that would come from each layer to the detector at certain point on our modeled Earth. So to get the geoneutrino flux, you need to know the decay rate of the elements that produce your geoneutrinos, that production spectra, also your abundance, the density, distance from each layer and elements that you're modeling to the detector, as well as something called survival probability, because neutrino is a very interesting particle that it oscillates. So we can only detect those electron antineutrinos, and sometimes a neutrino, when it flies, it decides to be a muon antineutrino or tau antineutrino. So you have to account for the fact that it can oscillate in different flavor to the different flavor neutrino. I need to know how many of my created electron antineutrinos will, by the time it reaches my detector, will still be electron antineutrinos. So when you do all this calculation, what's really interesting is that you find, and this is picture for KAMLAND, that with the nearest 500 kilometers around the detector, mainly the nearest crust, you get about 50% of your expected geoneutrino signal. So to really be able to tell anything about the mantle, deeper layers of the Earth, you really need to very well understand your near crustal geology. So then you can actually, from your total flux, count out your near crustal geology to be able to tell something about mantle or other layers that you are interested in. So that's a key component to first have really good model of the area around the detector and near crustal models to be able to say anything. So I'm trying to click. Here we go. So let's move on to looking at some experimental results that already been done by KAMLAND and BOREXINO. So I just want to show you what they look like and note some things about them. So both of the experiments have their similarities and differences, but the detection method still remains equivalent, where you have your scintillating material and it's surrounded by a layer of those photomultiplier tubes that can detect light. And then also each experiment has their different layers of shielding. So here, you have a shielding of water that tries to shield from the backgrounds that you don't want to see. So what's very interesting about them geologically, that their geological setting is different. BOREXINO is in Italy, and this position has larger contribution from continental crust, and KAMLAND is set in Japan, where you have larger portion of oceanic crust surrounded the detector. Therefore, having measurements from different settings actually is very complementary to each other. Having multi-site measurements, more multi-site measurements would be great for testing the predictions, as well as testing homogeneity of the mantle composition, given enough statistics and data, of course. Another difference between the two experiments is that we get antineutrinos also from the reactors, and their reactor neutrino background is really a large portion of a background that prevents really good geoneutrino measurements. So In this case, KAMLAND was primarily built for purpose of detecting reactor neutrinos, and has a large reactor neutrino background, whereas BOREXINO had focused more on the solar neutrinos coming from the sun, and they were further away from reactors. So you'll see that the backgrounds are a little bit different from them when I'm showing them. So just a brief history for geoneutrino measurements is summarized here. I believe this plot was made by Andrei Schramek. I had his name here somewhere, but I think it's on a different slide. This is a plot that shows a measured geoneutrino flux in TNU, which corresponds, it's a terrestrial neutrino unit, and it corresponds to one geoneutrino event recorded over a full year of fully efficient exposure of approximately 1 kiloton of liquid scintillator in the detector. So you can see that the first measurement for geoneutrinos was done by KAMLAND in 2005, and then was followed by BOREXINO in 2010. And you can see the trend of both experiments in the flux. They're quite in agreement, both starting very similarly with larger uncertainties, and as they got more statistics, they narrowed down their flux. And you can see that in terms of the flux, their values agree pretty well, in my opinion. It won't be quite the same when you account for geology later. So now this is quite a bit of physics, but I'll try to summarize a little bit. Here we can see a stacked plot to compare of 1,167 inverse beta decay candidate events fitted to the expected geoneutrino and the background, like reactor neutrinos here in white and some other backgrounds. From these 1,167 candidate events, they found that they have about 168 geoneutrino events with quite a large uncertainty. And then for the BOREXINO, they have spectral fit of 154 candidate events over their lifetime. And they also fitted their different backgrounds here. And they found 154, from 154 candidate events, they measured 52 geoneutrino events as well with the uncertainty. So mainly largely dominated by statistical uncertainty for these. Another notable thing is the KAMLAND's slow reactor data. So I like this plot a little bit, where you can see where reactor neutrinos are just overwhelming the geoneutrinos here in blue, but at the low reactor period, geoneutrinos actually peak out and are not so overwhelmed with reactor neutrinos. And from this KAMLAND data, you can see the spectrum of geoneutrinos pretty well. So during this, they were able to not only just detect the flux of geoneutrinos, but also fit the uranium and thorium portions of the geoneutrino separately to give a constraint for uranium and thorium ratio. So for a little geological interpretation, here the plot shows the geoneutrino flux versus radiogenic heat in terawatts coming from uranium and thorium. And these colorful contours show the possible flux values for different proposed models. So here, low Q, mid Q, and high Q stands for low radiogenic, so 10 terawatt, 20 terawatt, 30 terawatt Earth. And then the fully radiogenic scenario stands that what if we had no primordial heat anymore and all of the heat is radiogenic heat? So these values then, if you look at the gray value here, this is the this black line here shows KAMLAND's measured flux with this gray band of being 68% confidence level. And then if you look at this, their expected value for radiogenic heat comes to be around 12.4 terawatts. As well, here they did as also fit for the uranium and thorium ratio, and for that they got 5.3 of thorium over uranium, which is nice. And for the BOREXINO geological interpretation, we have similar plot. However, here they did not plot the total neutrino signal, but they did plot a signal coming from the mantle. And this plot has already had subtracted their expected contribution from the crust using their own crustal model prediction that they've done. So that's also an important point to note. And here again, in the y-axis, we have the geoneutrino signal in terms of the TNU. And on the x-axis, we have the radiogenic heat from uranium and thorium and terawatts from the mantle. And all these contour plots here show all the bulk silicate Earth models for low radiogenic heat to the high radiogenic heat or full radiogenic heat. And you can see with this gray band here, it's the GeoNu signal for the mantle in the region of with the region of uncertainty of 34%. So if you trace the median value, you get the corresponding 24 terawatts coming from the mantle itself, which is mainly consistent with highly radiogenic Earth model. However, measurement is also compatible with mid-Q model as well of 20 terawatt Earth and even fully radiogenic Earth. And it's technically compatible with all models. However, it starts rejecting the low radiogenic heat model within 2.4 sigma, which in particle physics, that's not enough to really reject the model. You need maybe like 5 sigma in particle physics to reject any models. So, but it's curious of seeing the difference between the two experiments. So then so this is a slide that I took from Andrei Schramek, and he did a little bit of summary and comparison of BOREXINO and KAMLAND results. And he plotted in the y-axis, he plotted the total measured GeoNu and TNU from each detector. And on x-axis, he had the expected signal from lithosphere, which is crust with upper mantle, depending on the model that of his. And you can see that then when you trace this line, you can actually determine how much in terawatts of radiogenic power you expect from both of the measurements. And from his calculations, he saw that for KAMLAND, it corresponded to 15 terawatts in the Earth, and with 8 terawatts left for the mantle. And for the BOREXINO, he saw that it corresponded to 38 terawatts in the Earth, with 30 terawatts coming from the mantle. So that's quite a large factor difference for the mantle contribution. And there's still ongoing efforts to understand this discrepancy, with some groups looking into the local crustal models. And recently there's been publication by my dear friend Laura Salmon and Bill McDonald, who's in the audience right now. So in their paper, they discuss some of the lithologies that were not included in the initial report by BOREXINO calculations that they thought they should have included. And once they revisited the geological models, especially of the near crustal composition, the combined analysis from BOREXINO and KAMLAND both seemingly favor models that are closer to the 20 terawatt of the present day radiogenic power in the Earth. So, which is really interesting. However, I'm of the opinion that we need more data and more statistics to really be able to distinguish between these models, especially when two amazing detectors are sort of a little bit at odds. So I'm hoping that with my experiment, Snow Plus, which, as I mentioned right now, we're taking the data here in Canada. I hope to in the near future report another measurement, and hopefully we can redo this analysis, including Snow Plus, and maybe something will be a bit more clear. So I'll just summarize that, there's still a lot to discover about the Earth, and geoneutrinos hopefully can help us answer some of these questions about radiogenic heat and the distribution of radioactive elements, as well as I hope we get more statistics, not just from Snow Plus, but in upcoming experiments that are still in R&D, to be able to add to the BOREXINO and KAMLAND measurements and help geoscientists to answer some of the very good questions that we still have. So thank you very much. I'm very glad that I was invited to present. So that's the end of my presentation.